important. I mean, there is a version that works in positive characteristic as well, but that's what I'm proving over k equals k bar. And then if y is a curve and a general fiber, i.e. the geometric generic fiber of f is rationally connected, then there exists a section. So every rationally connected fibration over a curve has a section, and there was a reduction. I mean, well, first there were some hypotheses. The first hypothesis was essentially harmless, just a simplifying hypothesis. Y is some curve. Let's assume y is P1. That's really not a very serious hypothesis. But then there's a second hypothesis which really is serious and needs to be justified, which is there exists a curve C in X such that, well, two things. One is that f of C is equal to P1, so it dominates P1, but that will be true of most curves in X, so that's not such a big condition. The real condition is that every point P in C is a smooth multiplicity 1 point of the fiber, XP, the scheme theoretic fiber of F over FP. So this is just defined to be F inverse FP. But then, assuming that we have one of these curves, then the strategy is to look at the space of deformations of this curve. So we can form some parameter space. I mean, just using Hilbert schemes, we can form some parameter space. Mg x beta, G is the genus of this curve, and beta is the curve class. So, I mean, if we fix some ample invertible sheaf on X, you can think of beta as just being the degree of the curve, of the class, of the curve with respect to that ample line bundle. So, curve class of C, and this is, again, curves, say smooth curves, smooth genus G curves in X with class beta. So, I mean, again, it's a truism of algebraic geometry that the parameter spaces for algebraic objects are, again, algebraic varieties, and this is just one instance of that. And then there's this other space, Mg P1 D. So now D is the degree of the restriction of F to C. So D equals the degree of this finite morphism from C to P1. And this is the set of covers, I mean D-sheeted covers of P1 by genus G curves. And this map, P, it's just the map that sends the class of some, so if we have some curve in X, so we have some point in that first parameter space, then we define this to be the class of the cover where we simply restrict F to C. And that gives us a cover of P1. So this is this map. And there's one classical result about this space, which is that it's irreducible. So Hurwitz proved that Mg P1D is irreducible. This is actually a result about an action of the braid group of P1. So, I mean, how many, by Riemann-Hurwitz, the number of branch points is 2G plus 2D minus 2 for this covering. And Mg P1D, a general point, will be a simple branch cover, so all branch points will be distinct and simple branch points. And then there's a map from MGP1D to the space of B tuples of points in P1. You have those B branch points. And the fiber of that map is something that you can understand topologically. And then the fundamental group of P1 to the B minus all of the big diagonals, that's the braid group that acts on the fiber just by monodromy, just by analytic continuation. And then Hurwitz proved that that action acts transitively, and that implies that this space is irreducible. So this space is irreducible, and then this is one observation. The other observation is that if we choose an arc, we can find arcs inside of MGP1D, and by arc I mean like an affine curve inside of this variety, such that when we look at the limit, so there exist affine curves, say A sitting inside of A bar, so sitting inside of the projective normal curve, the projective normal model. Inside, so A is inside MG P1D, such that, so the points of A parameterize a family of covers of P1. We can find one parameter family of covers of P1 such that in the limit, so if we take one of the points in A bar minus A, one of these missing points, then the cover we end up with, so it won't be a cover by a smooth curve. I mean, we don't want it to be. The point of cooking this up is that the corresponding cover of P1 has an irreducible component. So let me call that C double prime to P1 has an irreducible component, C double prime 0, which maps isomorphically to P1, so that this map is an isomorphism. So again, let me just draw a picture of that to show you what's going on. It's easier if you just start with the cover. Let me go over here since you won't be able to see that. So we can start, I mean, we could do this, we can in fact make this true for every irreducible component. So you can just choose D copies of P1 and glue them together. So D copies of P1. Glue them together at D minus 1 points, so D minus 1 nodes. So you take a reducible curve with D minus 1 nodes, and each one of these nodes counts for 2 of those branch points, and B is bigger than or equal to 2D minus 2. So we're only using up 2D minus 2 of these nodes, and then, I mean, for the remaining 2G, just identify G points among these curves. I mean, it doesn't matter. So, I mean, you can get this kind of a cover of P1 where, again, every irreducible component has this property that it maps isomorphically to P1. And then you can smooth this thing. And that's, again, by the Riemann existence theorem, you just have to prove that topologically you can smooth each one of these nodes. And, I mean, if you want to see why that's true, imagine you take a point in P2 and you look at projection away from that point. Then locally, one of these things looks like a union of 2 lines. And, of course, a union of 2 lines in P2 smooths to a conic, which then projects 2 to 1. 2 to 1 to the quotient of P2 by this point P. So this is projection from P. So again, this fact, I mean, this is just by the Riemann existence theorem, this is just a local topological fact that you can smooth each of these nodes. This proves that you can smooth each of these nodes. And then irreducibility, I mean, so that gives you this curve inside of MGP1D such that when you pass the limit, you get a curve like this. And then irreducibility of MGP1D says that if you take a general point in MGP1D, you can find one of these curves A that contains that point and has this property. So irreducibility says that this A can be chosen to contain a general point of MG P1D. I mean, what we're worried about is that MG P1D might have more than one irreducible component. And then maybe there's some point sort of in the boundary here that parameterizes these kinds of covers, and we're producing these little curves inside of MG P1D that limit to this guy we have to, like, this cusp or something. But we can't get these things to be on this irreducible component, so that would be bad. But luckily, Hurwitz proved that his space, this Hurwitz space, is irreducible, so we don't have to worry about that. So because of this, it will suffice to prove that that map phi is surjective. So claim to prove the theorem suffices to prove, in fact, it suffices to prove phi is dominant, that the image of phi contains a non-empty Zariski open subset. And why is this? Why? Well, we can take this, so we have that affine curve A, and we can make it pass through a general point. So if the image of phi contains a non-empty Zariski open subset, we can make that curve A intersect that non-empty open subset, and then we can find a curve sitting inside of mg x beta, which sits above that curve. So Y will assume, because image of phi contains a non-empty open, and we can make that curve pass through a general point, we can arrange that A intersects that non-empty open in a non-empty set. So it intersects the non-empty open. And then you restrict this morphism phi over A, and because the image is dense, we can find a curve in X. So there exists a curve A tilde in X, in mg x beta, mapping to a dense open in A. So the picture is we have this A tilde. It maps to some dense open inside of A. And now this thing sits inside of its projective normal model. This tilde sits inside of its projective normal model. And then by the valuative criterion of properness, this extends. And now choose any point up here that maps to this point T here. So, the image is dense, but this is a map of proper curves, so the image is also closed. So the image is all of A tilde, so there exists some T tilde that maps to T. That will be a curve inside of X whose corresponding cover of P1 looks like that. So some irreducible component of that curve maps isomorphically to P1. So the corresponding curve C double prime tilde, say, in X, or the curve corresponding to T, to T tilde, has an irreducible component. Just the component, C double prime tilde is essentially C double prime, has an irreducible component, C double prime tilde, mapping isomorphically to P1. Then you invert that isomorphism, and that gives you the section S that you want. So this was, I said this very quickly last time, but this is, how do I do this? So I don't think I can. So this is the reduction to proving that phi is surjective. So it suffices to prove that phi is surjective. That phi is what? Finite. No, phi is not. Phi is not finite. We don't know whether phi is finite or not. All that matters is that phi is dominant. If phi is dominant, then it contains this non-empty open subset. No, no. I just want to find some curve that maps A tilde inside of here that maps finitely to A. But it doesn't have to be the inverse image of A. The inverse image of A will be some variety that surjects onto A, and then I can just intersect that with hyperplanes and find some curve inside of there that maps finitely to A. And that's all I need. So, but the real issue is we don't know that phi is surjective. So what this argument shows is that it suffices to prove phi is dominant. And now, I mean, I guess this is the real place where we're using Hurwitz's irreducibility result. To prove that it's dominant, it suffices to, well, I mean, it suffices to prove that its image contains some non-empty open. So it suffices to prove this. To prove this, it suffices to find a single point, C in X. So this will be some point in mg x beta. We need it to be a smooth point of this variety. So this variety will not be smooth, but I mean, a generic point of this variety is a smooth point, such that the derivative map at this point from the Zariski tangent space of mg x beta to the Zariski tangent space of mg p1d is surjective. And let me leave some space here. The point is, now we can identify what each of those two vector spaces are. So, I mean, we have these two finite dimensional vector spaces. What are these things? So if you take a curve inside of a variety, then the first order deformations of the curve inside of the variety correspond to global sections of the normal bundle. So, I mean, if you imagine that you have a surface inside of your variety that contains the curve as one fiber, the surface is fibered over some base, contains the curve as one fiber, you have a map from the tangent bundle of the surface to the tangent bundle of X, and you have the normal bundle of the curve in the surface as the trivial bundle, so it's O, and that will map to the normal bundle of the curve inside of X. So you get a map from O into the normal bundle of the curve inside of X. In other words, you get a global section of the normal bundle of the curve inside of X. So this thing is just the global sections of the normal bundle of the curve inside of X. This thing is kind of interesting. I mean, this comes back down to understanding this Hurwitz space. To deform the cover, you just deform the branch points. How many branch points are there? Well, there are B, the number you get from the Riemann-Hurwitz theorem, but that's also equal to the length of, you take the pullback of TP1, well, restricted to C. So that's a locally free sheaf on C. You mod out by the tangent bundle of C. So this is now a torsion sheaf. I mean, this map from TC, the derivative map from TC to this pullback, is an isomorphism at every point that's unramified. So this is supported on the ramification points, and it's a skyscraper sheaf on the ramification points. So, well, I mean, if the ramification points are simple. So this is equal to this guy. So we have this map here, and again, this is some torsion sheaf. This is equal to a quotient of the torsion sheaf, which is simply take the normal bundle of C at X, and then restrict that to the points, I mean, the normal bundle of C and X, modulo the ramification divisor. So restricted tensor with O of the closed subscheme, the finite subscheme of ramification points. So we can take NC of X, we can restrict it to the ramification points. That will give us a torsion sheaf. This guy is a quotient of this. And of course, we have this evaluation map. So this breaks up this thing. We would like to prove that this map is surjective, so it will suffice to prove that this is surjective. So again, let the ramification divisor be denoted R. Then we have a short exact sequence. One of these boards is not coming down. Okay, I'll use those ones. So we have this short exact sequence expressing this map as a map in cohomology associated with that short exact sequence. It's just you twist the normal bundle down by R. So we have the normal bundle of C and X minus R to the normal bundle of C and X. And then this thing, the normal bundle of C and X, tensor with O of R to 0. And then we take global sections, so we get, I mean, the important part is this one. And then there's some connecting map to H1 of this guy. So if we prove that this guy is 0, then it follows that this map is surjective, and then this map is a quotient of this map, so it follows that that map is surjective as well. So it suffices to prove that H1 C in Cx minus R is equal to 0. So now R is some divisor of length, of degree b. So we'll actually prove this. We'll prove that. So now this, okay, let me just point something out. We started with this hypothesis that there exists this C with this property. Almost certainly this fails. For that particular choice of C, this fails, but we'll cook up a new curve C where this holds. So now the strategy is build a new curve C prime from C where this holds. So let me just say a couple of things. The new curve C prime will have the same genus as C. The map from C prime to P1 will have the same degree D. The curve C prime will not be the same curve class, but it will differ by adding curves in fibers, rational curves in fibers. So that won't change the genus and it won't change that D. The size of the ramification doesn't change either. So in fact, we're going to produce a new curve, C prime. Well, we don't know what the ramification for this new curve is. We'll produce a new curve C prime from C, where for every divisor R of degree B, H1 C prime minus R is equal to 0. And then, of course, the ramification divisor for the map from C prime to P1 will be one such divisor. The size of that divisor, B, depended only on G and B by the Riemann-Hurwitz theorem. So that's what we're going to do. And how are we going to do this? So this is something, this construction, building a new curve from this old curve, is one of the basic techniques. It's the cone construction. It was known, the idea of this construction was well known for quite some time. So it's a cone construction. So we have this X with this map to P1, and then we have some curve C inside of here doing something. And what we're going to do is we're going to choose a bunch of points, a large number of points, general points, say P1, P2, up to some PR. And for each one of those points, we'll attach a rational curve in the fiber. So remember, the fibers of the map from X to P1 are rationally connected, and rationally connected varieties have these very free curves, these curves. So let me give names to these curves. So this will be D1. We'll attach one of these at each of these points. dr minus 1, dr. So each dr is a curve in the fiber X of f of pi containing pi. And also remember, we can also choose the tangent direction if we want. And with specified tangent direction. I'll mention why we want to do that in just a second. Specified tangent direction, Vi, such that the pullback of the tangent bundle of the fiber, the tangent bundle of the fiber restricted to di, is ample. Remember, that means that, i.e., it's isomorphic to a direct sum, A1, some large number of these guys, where all of these ANs, these AJs, are positive. So every rationally connected variety has very free curves through any point and with any specified tangent direction. So we can find these di's. We'll make this highly reducible curve, and we call this curve D. So it has this one component, which is C, and then it has all of these vertical components, D1, D2, up to dr. And this, of course, is not a point in mgx beta, which isn't up there anymore, because that only parameterizes smooth curves. So we want to do two things. One is we want to guarantee that this curve deforms to a smooth curve. So I can't do it. Okay. That board is stuck there. I'll be there for the rest of the lecture. So we want to deform this curve D, and then we want to a curve C prime, and we want to guarantee that that curve C prime satisfies the condition. So deform D and ensure, so to some C prime, and ensure C prime satisfies the condition. So can we deform D? So this is, so this cone construction was well understood. You can look at the problem of deformations. The deformations may be obstructed, but it turns out that, so there's some Zariski tangent space to some Hilbert scheme at this point. Parameterizing not just smooth curves, but also arbitrary subvarieties of the total space X. You can look at the Zariski tangent space. Those are first-order deformations. Not all of those first-order deformations extend, but there's an obstruction to extending, which lives inside of some obstruction group, which is some vector space of finite dimension, which is independent of the number of points you would glue on. So as you glue on more and more points, the Zariski tangent space grows in dimension, whereas the obstruction space doesn't. So eventually, you have more deformations than obstructions, and therefore you can deform. So one of the basics of this thing is that as long as we glue on, as long as we attach sufficiently many di's, then D deforms to a smooth curve. Or let me say more precisely, it deforms to a family of smooth curves. We can find a one-parameter family script C prime over some base curve S, such that for some point inside of this curve, we just get D. But for a general point inside of this curve, little s, we get a smooth curve, C prime. So that's the goal. We show that after gluing on enough of these vertical components, this curve D deforms, so it's a specialization of a family of curves, such that the general member of this family is smooth. So that's the first condition. We want to guarantee that D deforms. But now what about the second condition? So this is this is what makes this work. So this is the whole point of this construction. The normal bundles, so even though this is a reducible curve, it's singular, it still has a well-defined normal bundle. And the normal bundles are vary algebraically. So there is a normal bundle of D in X, and the normal bundles of the fibers form a locally free sheaf on this total space C prime. So by semi-continuity of cohomology, to prove this statement that the H1 C prime, C prime will be a general fiber of this thing, equals 0 for general C prime equals C prime T. It suffices to prove this for D. Let me just point out one thing. So let me draw a picture of this. So we have some family of curves over some base S, where the central fiber is this highly reducible curve, C and then these D1 through DR, and then this is the general fiber, C prime, over some point T, and this is over 0. And we can look at if we restrict F to these curves C prime, and we look at the ramification points for that finite map from C prime to P1, then for each of these fibers we get some number of ramification points. As we vary the fiber, those form curves. And the question is, when they intersect the central fiber, where do they intersect? They exactly intersect at the branch points of the morphism from C to P1. So they don't ever land on one of these components di. So remember, we're going to twist this thing down by these points. That means that when we look at this condition on D, we're only twisting down by points on C. So we want to prove that after attaching enough components, we can arrange that this thing vanishes for every divisor of, well, in fact, we only need to do this for the ramification divisor for the original map. So doing this, we can certainly arrange it for every divisor of degree B. We only need the ramification divisor. But we don't have to worry about these DIs. And now, this is a very simple cohomology computation. The point is that, the normal bundle, it's hard to think about the normal bundle of a singular variety in a smooth variety, like the normal bundle of a union of two lines in P2. That's a degeneration of a conic. You have the normal bundles of irreducible components separately, and then you have the normal bundle of the total curve. So if we take the normal bundle of the total curve in X and restrict it to one of the irreducible components, say C, then how does this relate to the normal bundle of C in X? So this is equal to the sheaf of rational sections, so meromorphic sections, of this guy with a pole, with poles at the points P1 through PR in these tangent directions, in the tangent directions VI, in the tangent directions VI. So what this means is we can make this, after attaching a lot of these vertical curves, we can make this new bundle much more positive. We're twisting it up in one direction for each of these PIs, and we get to choose the directions, and we get to choose the points, generally. So eventually, we can make this as positive as we like. And positive bundles on varieties tend to have no higher cohomology. So because we can make this as positive as we like, we can arrange that H1 of C in dx minus R is equal to 0. Now, of course, that's not what we're looking for. We're looking for H1 of D in dx, but there's a short exact sequence. We have the direct sum over all of the di's of the normal bundle of D in X restricted to DI, and then twisted down by the point PI to the normal bundle of D in X, and then this thing, the normal bundle of D in X restricted to C, twisted down by R. Oh, I'm sorry, this is twisted down by R as well, to 0. So when you look at the long exact sequence of cohomology, to prove this H1 is 0, it suffices to prove this H1 is 0, and this H1 is 0. Making this H1 0 is the whole objective of attaching all of those vertical fibers. So this one, we know that H1 is 0 by this board. And now for these guys, the normal bundle of D in X is equal to, restricted to DI, this is a little bit more positive than the normal bundle of DI in X. So it suffices to prove the normal bundle of DI in X, twisted down by minus PI, has no H1, because this thing sits inside of here and the quotient is torsion. This thing is the normal bundle of DI in its fiber, X of F of PI, direct sum, a trivial bundle. And now we take that and twist down by P. So this is isomorphic to O of minus 1 on P1. And O of minus 1, even though it's negative, it has no H1. So because O of minus 1 has no H1, and this is even, this guy was positive, so this is at least globally generated. This also has no H1. So neither of these have H1. So H1 of this is 0 as well. And then by the long exact sequence of cohomology, that implies that H1 of this is 0. And that's what we needed for this curve C prime. So that proves that when we deform D to the C prime, that H1 is 0, which then implies that D phi is surjective. So for C prime, so therefore, for C prime, D phi at C prime is surjective. finishes the proof, I didn't prove for you that there exists this curve C. I mean, we made this very serious hypothesis that there exists a curve inside of the smooth locus of the morphism from X to P1. That has to be justified, but it's the same sort of argument. You do the same sorts of constructions. You allow yourself one more maneuver, which is to glue on these very free curves that connect 2 points. The point of that is that that allows you to make the topology of this curve a little bit, I mean, it gives you more branch points, B. I mean, for each one of these curves like this, you pick up 2 branch points, and you can control the monodromy around those branch points. So there's some little topological argument to prove that this C exists. But it's very similar, so let me just skip it. So that was the theorem that I wanted to prove yesterday, and now today, I will not have a chance to prove this completely, but I'll just sketch the main ideas. I want to show how this kind of reasoning can be carried forward, not just to fibrations over curves, but to fibrations over surfaces. So what about fibrations over surfaces? Well, are there any questions about this argument? So the idea of the argument, the motto, is just that we want to prove some H1 is 0, so we want to make the vector bundle more positive, and this comb construction exactly allows you to do that. That was well understood before, that if you glue on a bunch of curves where the vector bundle is more positive on those curves, then 1, if you glue on enough of these curves, the reducible curve deforms to a smooth curve, and 2, if you glue on enough of these curves, the vector bundle on the new deformed smooth curve will be as positive as you like, and then that gives you that the H1 is 0, which gives you surjectivity of phi. So that last part about the comb construction was well understood before this. So what about fibrations over surfaces? Yeah. Well, one of the places I used that the characteristic is 0 was irreducibility of the Hurwitz scheme. So in characteristic 0, all ramification is tame. But in positive characteristic, the space of covers of P1, well, maybe for P1 it's irreducible, but in general, if you allow non-tame ramification, then you have to worry. That's actually not a very serious concern. I guess the one thing that argument that proved that if you have a rationally connected variety in characteristic 0, then there exist these very free curves. I mean, we proved that yesterday. You just deformed the 2 points. But that sort of argument doesn't work in positive characteristic because you can have a surjective morphism such that the derivative at every point is 0. I mean, that argument that showed existence of very free curves was essentially that some derivative map had to be surjective, and then you look at what that says, and it tells you some curve is very free. But that doesn't work in positive characteristic. And in fact, there are counterexamples. So there are K3 surfaces that have no free rational curves at all, but nonetheless are rationally connected. So they've got plenty of rational curves. It's just none of them have this property about the tangent bundle being positive or even globally generated. So that was the more serious place that we used. This local criterion, I mean, in one direction it works in positive characteristic if you have very free curves, but we were using the other direction, that if you have a rationally connected variety, then there exists very free curves. But if you assume that your varieties have very free curves, then the argument does go through in positive characteristic. So there is a version of this argument that works in positive characteristic. You have to replace this rational connectivity by the stronger hypothesis of existence of these very free curves. And you have to do there are a few other little places where you have to do something different in positive characteristic as well. But that's the main difference. Are there any other questions? No. So fibrations over surfaces. So the idea is just to reduce this to the case of fibrations over curves. So I'm going to just sort of explain the strategy at the same time as explaining why this implies the period index theorem. So let me remind you what the period index theorem says first. So we'll have some surface. So now y will not be a curve, it will be a surface. And then on this side, we'll have some D, a division algebra with center is the function field of the surface. Now, given such a thing, so there are these two invariants, L, the period of D, which is equal to the order of this element in the Brouwer group of the function field. So This is a torsion group. Every element has some finite order, so we just call that integer the period. And then there's another integer, the index of D. This is the unique integer n, such that when we base change to the separable closure, this is n by n matrices over that field. So, and then the theorem proved by de Jong is that for the function field of a surface, so y is a surface, the period equals the index. L equals n. So let me just point out right now how we're going to get a fibration out of this setup of a division algebra. The point is that we can let x be the Brouwer-Severi variety L of D. So this is the scheme. I mean, it's a scheme over y, but I mean, we really only care about this thing we really only care about the generic fiber of this thing. I mean, the argument I'm going to sketch sort of only cares about generic, well. So this is the scheme whose generic fiber over y parametrizes, represents the functor of right ideals in the space of matrices, represents the functor. So it's like the usual Severi-Brouwer variety. It represents the functor of right ideals R inside of D. But for the usual Severi-Brouwer variety, we look at right ideals whose rank is equal to n, and now we'll look at right ideals whose rank is equal to Ln, whose rank equals L times n instead of just n. But observe that if we base change to the separable closure of the function field, then this D is just the space of matrices. What are these right ideals of rank Ln? Well, if you choose an L-dimensional subspace of your n-dimensional space and look at all matrices whose image is contained in that L-dimensional subspace, that is a right ideal of rank Ln. And conversely, it's very easy to prove the converse. So after the geometric generic fiber of this thing is just the Grassmannian parametrizing L-dimensional subspaces of this fixed n-dimensional vector space, giving you the matrices. So the geometric generic fiber is a Grassmannian of L-dimensional subspaces in a fixed n-dimensional vector space. Or, you could think of it as quotient spaces if you like. So this is a twisted form of a Grassmannian over Y. But you can consider fibrations over surfaces more generally. It's just, this is the one that will lead to the period index theorem. And you can, unless n is equal to 2L, you can go backwards as well. If you have a Grassmannian fibration of scheme Y, then there exists a unique division algebra, or central simple algebra, excuse me, not necessarily a division algebra, such that applying this construction, you get that fibration. So this is just a generalization of that one-to-one correspondence from the first lecture. Generalized Brouwer-Severi varieties, these Brouwer-Severi varieties where you have that L, except when n equals 2L, they're in one-to-one correspondence with central simple algebras of index n. So now what are we going to do? The idea is to fiber the surface. So so far from that side, we only care about the generic fiber of this thing. So we could blow up Y, we can modify Y birationally, and that's not going to change the problem. So in particular, we could take a Lefschetz pencil of curves on Y, blow up the base points, and then fiber Y over P1. So we can fiber Y over some curve. Let me call that S. So this is F, this is pi. And now, so this is a curve, and this is a surface, and this is whatever it is. So sort of the picture might be something like this. So this is the surface fibered over the curve. And then we have some fibration over this thing. So this is X, F, Y. Now, we want to understand sections of Y to X, but it turns out that there's a space. Grothendieck constructed, as a consequence of the existence of the Hilbert scheme, Grothendieck constructed some space, pi x y over s, sitting over s. Let me draw it a little bit lower down. And this space has some universal property. There's a map from the fiber product of this S scheme and Y to X. I mean, a morphism of S schemes. Everything is over S. So there's some map, sigma, with the property that if we then compose further with F to Y, again, everything is over S. That's just the same thing as projection onto Y. So in other words, this is the space over S whose fiber over a point in S parametrizes the sections of X over Y. If we assume that F is a rationally connected fibration over Y, then we know if we take any point in little s inside of here, we look at the corresponding curve, Y sub s, we look at XS sitting over YS, then because this is a rationally connected fibration, we know there are sections. And the point is there's a space parametrizing those sections, and we call it pi. So this is the space of sections. Of F over S. So its fiber over each point in little s is the space of sections from X of the restriction XS to YS. So there's some section here, sigma YS. So there's some universal section. And now we want to prove that there's a section of this morphism that's equivalent. I mean, you have to think about this for a few minutes. That's equivalent to proving there's a section of this morphism. So to prove there exists So to prove there exists a section of the original F, it suffices to prove there exists a section of this pi map to S. And now that's good because S is a curve. So we can hope to apply this RC fibration theorem. I mean, if we have an RC fibration over a curve, we know there's a section. So this reduction shows that there exists a rational section of X to Y if and only if there exists a rational section of this pi xy over S to S. Again, pi is parametrizing the sections of the fibers. So if we find this section here, S, then the idea is, so why is this? If we have this S morphism to pi, let me call this map T, then of course we get a map from S cross SY, which is just Y, T cross identity Y, to pi. And then we can compose that with this universal sigma to X, and this composition will be the section we're looking for. And then in the other direction, I mean, this is, again, this is the whole point of this guy. So if we prove that this thing is a rationally connected fibration, so that there's a section, then it follows that we get a section here. So, I mean, it's not. I mean, it's not true. So you can't prove that this is a rationally connected fibration because it's not. The problem is that there are obstructions to the existence of sections of any morphism, even rationally connected morphisms, over a higher dimensional base. There was this Brouwer-Manin obstruction you guys saw last week. There's a much simpler version of the Brouwer-Manin obstruction. It's very elementary, so it's called the elementary obstruction. So did you guys see the elementary obstruction? Maybe you saw it as part of the Brouwer-Manin obstruction, but the point is that if you have some fibration over Y, and we'll assume that the Picard group of the geometric generic fiber is Z. This isn't really necessary, but that's certainly true for Grassmannians. Grassmannians, you have the Plücker embedding, and the line bundle for the Plücker embedding generates the Picard group. So this hypothesis holds for that generalized Severi Brouwer variety. Then the question, does there exist an invertible sheaf L on X whose base change to the geometric generic fiber is a generator for the Picard group? I mean, it's said another way, if you think of this geometrically, for every fiber over a closed point, there exists such a line bundle L, which is a generator for the Picard group, but it's not clear that those invertible sheaves on those fibers glue together. There might be some obstruction, there might be some topological obstruction, but
What is the subscript on X?
this is, I'm sorry, the geometric generic point. So we have eta y bar. This is, I mean, it's a morphism. It's spec from, we take the fraction field of ky, and then we take the algebraic closure. So this is the geometric generic point. But I mean, again, if you think geometrically, what this is saying is that if you take the fibers over closed points or over geometric points, then the Picard groups are Z. So for every closed fiber, we have this line bundle. It's going to be canonically defined on that closed fiber. But the problem is gluing these things together, there's some gluing data, which is an element in the units down here. So you get some cocycle in the units. So the obstruction is some element. In Étale cohomology, the obstruction is an element, omega, in the Brouwer group of Y. Well, I mean, let's say, does there exist L on X restricted to some F inverse of a dense open? So on any dense open, not necessarily all of Y, then this is an element in the Brouwer group of the fraction field, which partially explains why I didn't have to talk about this before. Before we were talking about the case where Y was a curve, and then Sin's theorem says the Brouwer group of a curve is trivial. So if Y was a curve, this would automatically hold. But when you have a higher dimensional base, like a surface, this doesn't automatically hold. But the whole point here is that omega for the generalized Brouwer-Severi variety, by just a simple computation, equals L times the class of D inside the Brouwer group. So if we make L be equal to the period of D, then this obstruction vanishes. So for L equals the period of D, I mean, the smallest integer such that this is 0, the obstruction vanishes. So there does exist one of these things. So now we have this invertible sheaf L on X. What does that, why am I doing this? What does that buy us? The point is that this will now determine a morphism. So I said that pi is not rationally connected, and let me tell you why it's not rationally connected. So pi parameterizes sections of y sub s to x sub s. For each such section, I mean, we have this invertible sheaf L on X. We can pull that back by that section. So we can take sigma upper star of L on pi cross y. This is an invertible sheaf on y, so it defines a morphism. This determines, I mean, the functor of invertible sheaves is represented by the Picard scheme. So this determines a morphism, I mean an S morphism from pi to the Picard of y over s. So, and this thing sitting over S is certainly not rationally connected since its fibers are, I mean, countable disjoint unions of abelian varieties. So this is absolutely not rationally connected. And since this thing maps to this thing, I mean, if you take 2 points here that map to different points here, there are no rational curves in any abelian variety. It cannot possibly be that this thing is rationally connected. So it follows that this is not rationally connected. So it seems like this whole strategy just broke down, but it doesn't. I mean, the point is that the relative Picard certainly has sections because there are line bundles on Y. I mean, Y is some projective scheme. There are plenty of line bundles. So there are sections. What we need to know is not that pi is rationally connected over S, but that the fibers, so there exist sections U from S to pick ys. Let me break this up. So, I mean, a line bundle on a curve has a degree. This is the family of Picard schemes of those fibers y sub s. So there's a degree. So this breaks up according to the degree of the line bundle. I can just define pi sub e to be the inverse image of this connected component of pick inside of here, and I'll call this alpha sub e. So there exist sections E for E sufficiently large and divisible. I mean, in fact, we can choose it. We can choose E as 1. I mean, we had that Lefschetz pencil. So the exceptional curves give degree 1 invertible sheaves. So there exist sections like this. So now what do? We restrict this morphism over that section. So we take alpha E inverse of U of S. That maps to U of S. But of course, U of S is just isomorphic to S as an S scheme. So and this is, say, let's call this pi E U. I mean, yeah. So if this is rationally connected, I mean, this is a curve. So if this is rationally connected, there's a section. So saying that this is rationally connected is the same thing as saying that the fibers of this are rationally connected is the same as saying the fibers of this are rationally connected. So if alpha E has rationally connected fibers, this is an RC fibration over a curve, and therefore it has a section. So it has a section. T. So let me put this up. So now we can compose U with T, and when we compose U with T, we get this section. Oh, I already used the letter T. Sorry about that. So that section should, that second section, call that V. Let's call that V. Sorry. So there exists a section V. And then U composed with V will be T. So to finish the theorem, it suffices to prove that the fibers of alpha are rationally connected. So if there exists a rational section V of pi U to U of S, then, so that's this V here, then V composed with U. So U maps S to U of S, and then V maps U of S to pi. So that's a map from S to pi, which is a section S of this projection to S. So it suffices, so because of this, the whole point is that it suffices to prove that the fibers of alpha are rationally connected. So it suffices to prove fibers of alpha are rationally connected. Also, I realize I'm going to be out of time in just a second, but this also explains the importance of this obstruction. I mean, this obstruction is maybe non-zero if you take, I mean, for this choice of L, it is 0. But imagine we chose the wrong L, then this obstruction would be non-zero. But so what? I mean, some power of it, some multiple of it is 0, which means there exists some invertible sheaf L whose base change isn't necessarily a generator, but is some multiple of a generator. So why not just use that in constructing all of these things? But the point is that if you do that, if you look at the fibers, then that would factor through the multiplication by, if you used M times a generator instead of the generator, that would factor through the multiplication by M map here. So this thing doesn't even have connected fibers, so alpha can't possibly have connected fibers, so they couldn't possibly be rationally connected. So this is the geometric significance of this obstruction. If you choose the wrong invertible sheaf, alpha won't even have connected fibers, so it certainly won't have rationally connected fibers. So to have a chance at proving the fibers of alpha are rationally connected, we need to choose the correct L, which means we need that elementary obstruction to be 0. So this is why, that's why the elementary obstruction is actually important. So just remark, this has disconnected fibers. So that's just an aside. So now let me finish off the proof. The point is, first of all, this now has nothing to do with S. I mean, it's just all on alpha. We want to prove alpha has rationally connected fibers, so we choose some point and pick y over S. That point maps to a point in S, so we can base change from S to just a geometric point in S. So replace S by a geometric point. I mean, say the geometric generic point, little s of S. Again, we're trying to prove that the fibers of alpha are rationally connected, but this was all functorial over S. So to prove that, I mean, the fibers of alpha for that S will be the fibers for a base change, so we can replace S by we can base change to a geometric point of S. So now we have XS to YS, and this is a curve. So now we have this vibration over a curve. We have this pi XS YS to pick of YS. So this is the Jacobian of some curve. We have this alpha map here. So what is this? Well, this is now where I'm going to cheat. And so there should be some completely general argument that will tell you rational connectedness of alpha if you assume some very nice properties about x over y. Essentially, that this is rationally connected, and the space of rational curves and fibers are also rationally connected. So this is the analog of simple connectedness. Simple connectedness in topology says not only is your space path connected, but the space of based paths is also path connected. So rational simple connectedness should be not just rational connectedness of your variety, but also rational connectedness of the space of based paths, which are rational curves in your variety passing through 2 points. That's going to hold for the Grassmannian, but let me just cheat because we're out of time and I want to finish this up. The point is that D restricted to y of s is end of a vector bundle by Sin's theorem. Division algebras, central simple algebras over the function field of a curve are all just matrix algebras. So this is end of some vector bundle, a rank n bundle. Now these right ideals, they correspond to locally free subsheaves of rank L inside of S. So XS is equal to the Grassmannian of locally free sheaves. Locally direct summands, not just locally free, but the co-kernel should be locally free as well. The usual Grassmannian of E. This map alpha, so this parametrizes F's inside of E such that E mod F is locally free. F and E mod F locally free, and F has rank L. This map alpha, so the map alpha it's a Grassmannian fibration over y sub s. So, it's F inside of some point EY. Anyway, so it's a Grassmannian fibration over y sub s. But then what is pi? So we have this Grassmannian fibration over y, pi parameterizes the sections. In other words, pi xs, ys parameterizes these subbundles. So again, this is a vector subspace of a fiber, but now pi parameterizes the thing I wrote a moment. What is alpha? So alpha is the map that's F to its determinant. We have to end up with an invertible sheaf on y. And that's the most natural thing, and it's not hard to show that is exactly what this map alpha is. So alpha of F is simply the determinant of F. Now, E is minus the degree. E equals minus the degree of F. It would have been better if I'd set these up as quotients instead of subsheaves. But it turns out that if you let E be really large, so the degree of F to be really small, so this is fixed. It's some invertible sheaf M. Let me call it P on y sub s. So that we fix that because we want to look at the fiber. So pi xs ys E. It's these subsheaves F in E. The determinant of F equals P, and the rank of F equals L. The E is minus the degree of F, which is minus the degree of P. If you choose this to be really negative, then a general vector bundle with this degree will map to E. So this thing maps to the space of bundles with this fixed determinant on ys. And the fibers are Hom spaces. If you fix F, how many ways are there of F realizing F is a subspace of E? It's just Hom of Fe, which are rationally connected. Fibers are Hom Fe. So the fibers are rationally connected. Therefore, we want to prove the total space is rationally connected. By the rationally connected fibration theorem, it suffices to prove that this is rationally connected, but this is easily rationally connected. The point is that to give a vector bundle F of a fixed rank and determinant, you can choose some hugely negative line bundle on your curve. Take this thing to the L plus 1. If this is sufficiently negative, a general vector bundle F of rank L is a quotient of this thing, and then you have the kernel But this kernel, it's a line bundle, and it's determined by p. I mean, the determinant of this times the determinant of this is the determinant of this. Since the determinant of this and the determinant of this are fixed, the determinant of this is fixed, so this is fixed. So to get all vector bundles of rank L and determinant p, you figure out what this k is, and then you look at Hom. So this thing is a quotient of Hom, k, O minus 1, in direct sum L plus in 1. And of course, that's a vector space. So it's an affine space, so it's rational. That proves that this thing is unirational, therefore rationally connected. The fibers are rationally connected, so this fiber of alpha is rationally connected. And then by the argument, it follows that there exists a section, which means there is a right ideal inside of D, in the original D, of rank L times n, but the only right ideals in a division algebra are 0 in the whole thing. So L times n has to be n squared, which means L equals n. So there exists. I mean, there exists a section of that original x to y, which means there exists a right ideal I in D of rank Ln. But since this is a division algebra, that implies that I equals D. So Ln is equal to the dimension of D, which is n squared, which implies L equals n. But that's exactly saying the period, which is L equals the index n. So I apologize for running over. This is one example, but there's some part of this that's general and should work under much more general hypotheses. But this shows the main application, which is the proof of the period index theorem.
So what is N here?
If you choose a bounded family of locally free sheaves on a curve, then you can find a single very ample invertible sheaf O of n, such that when you take, so this is the dual of an ample invertible sheaf, a very, very ample, dual of a very ample. So what I'm claiming is if you take some bounded family of Fs, you can find a single very ample invertible sheaf such that every one of these Fs is a quotient of the dual raised to the L plus 1. I mean, you can do some Bertini theorem where you look at Hom of this guy to F and say, are there enough global sections so that this map is surjective? And by a Bertini type argument, if the dimension of the space of global sections is large enough, then yes. And if it's a bounded family, to get that space of global sections large enough, you have to choose O of n to be sufficiently ample. So it's just, this is how you present vector bundles on a curve. There is a presentation of this form. I mean, also, the moduli of stable vector bundles on a curve is a Fano variety. So if you use the theorem of Kolar, Miyoka, Mori, and Campagna, that also implies that the space of vector bundles is rationally connected.